Okay, so this is another video to support you learning from home. This is about chapter 4 on binomial expansions, which you've done in year 12 in the AS course, but this is an extension of that. So hopefully you've already got some good understanding of the year 12 binomial expansions. If you need to go back and review that, then do so. That's essentially expanding brackets of the form x plus y to the power of n, where n is a positive whole number. So if you're ready to, let's just practice one of those just to get you thinking along the right lines. You might want to have a go at this first on your own, and then I'll go through it. Okay, so to expand 3 plus x to the power of 4, it is going to be 3 to the power of 4 plus 4c1, which is 4. Let's write 4c1. You'll see why in a minute. Times 3 cubed times x to the power of 1. We're then going to have 4c2 times 3 squared times x squared. We're going to have 4c3 times 3 to the power of 1 times x cubed. And then we're going to have 4c4, which is just 1, times x to the power of 4. If we work these values out, 3 to the power of 4 is 81. We've got 4 times 27, which is 108. 4c2, you can check that on your calculators if you're not sure. That's 6. 6 9s are 54. 4c3 is 4. 4 3s are 12. And then x to the power of 4 on the end. So that's the expansion for 3 plus x to the power of 4. So I've got my answer there. Let's just edit this slightly. Let's work out 1 plus x to the power of 4. And not going to know why I'm doing this at the moment, but hopefully you'll see where this is heading. There's not going to be much difference, other than if we go back up to the top, these 3's that I've conveniently left in brackets here are all going to be 1s. So that's going to be 1 to the power of 4, which is 1. It's going to be 4 times 1 cubed, so that's just 4x. It's going to be 6x squared, 4x cubed, and x to the power of 4. Can we write something down if I change this 4 to an n now? If you look at what we've got here, you hopefully recognise these numbers. There's a 1 there. Let's write that in. They're the Pascal's triangle values for row 4. That's 4c1, 4c2, 4c3. Sorry, no it's not. That's a lie. This is 4c0. Oh my goodness. 4c1, 4c2, 4c3, and 4c4. Oh dear. .4c4. Okay, so what difference will it make if we do 1 plus x to the power of n now? Hopefully you can have a think about what that will look like. Obviously if it's an n, it's going to carry on until we reach n, but we can write something useful down for this. We're going to have 1. We're going to have whatever that n value is, c1x. We're going to have nc2x squared, nc3x cubed, and that's going to carry right on up until we get to NCn, which is 1, and we'll have x to the power of n at the end. So, why are we talking about this? Why are we doing this? Well, we're doing it because in year 2, our n value is not going to be a positive whole number anymore. It can be negative, it can be fractional, it can be a negative fraction, like minus 2/3 or minus 1/2. It can be absolutely any value. And we're going to learn how to expand those kind of expressions. Now the problem is when n is not a whole number, a positive whole number, these values, the NCR part, we can't work out with the calculator. We can't do a half C1, a half C2. It doesn't work. If you try it on your calculator, you'll get an error. But that doesn't mean that the expansions don't exist. All that means is that we are going to have to work out the NCR part of the terms ourselves rather than relying on the NCR function of the calculator. So what we need to do next is we need to go back a step or a few steps and think about what NCR is. What is the calculator working out when we ask for, say, 5C2? And if you think way back to year 12, when you first were introduced to NCR, it had a formula. And the formula was n factorial over n minus r factorial, r factorial. So something like 5C2 would be the answer to 5 factorial over 5 minus 2 factorial, so 3 factorial, times 2 factorial. And we can work that out. 5 factorial is 120, 3 factorial is 6, 2 factorial is 2, so that has an answer of 120 over 12, which is nice, that's 10. And you can check that on your calculator. You can check what 5C2 is, and if I've done my maths right, you should get an answer of 10. And you do. So, we're going to be able to do this. We're going to be able to apply this when we have fractions or negative numbers. In order to do that, we're going to replace NC1, NC2, NC3 with the cancelled down versions, kind of like what we've done here with the NCR values. So 1's just 1, that's fine. What will NC1 be? Well, if we write down the formula again, just so we've got it on the same page. NC1 is going to be n factorial over n minus 1 factorial times 1 factorial. So that doesn't look very helpful. We've got the x as well. That doesn't look very helpful, but it actually really is. Because if we think about what n factorial means, that means n times n minus 1 times n minus 2 all the way down to times by 1. N minus 1 factorial just starts 1 lower than this does. This will be n minus 1 times n minus 2 times n minus 3 all the way down to 1. And we've got a fraction here. So what's going to happen is these terms on the top, that n minus 1 is going to cancel with that n minus 1. That n minus 2 is going to cancel with that n minus 2. The n minus 3 that's sat here is going to cancel with this n minus 3 here. And the 1's are going to cancel. Not that the 1's are particularly important. So a lot of this is going to cancel down, and if we look at what we've got left, we've got an n times an x over 1 factorial. So we can write that our first term is going to be 1, and we can now write a better version of this, which will be n times x over 1 factorial, but 1 factorial is just 1, so I don't really need to write that down. Let's look at the next term. Let's look at nc2. That would be n factorial over n minus 2 factorial, 2 factorial, and then we've got rx squared on the end. N factorial, we know, we've just said is n times n minus 1 times n minus 2 times n minus 3, all the way down to 1. This term here now starts with an n minus 2 times n minus 3 times n minus 4, and so on. All the way down to 1. And again, we're going to have terms cancelling out. The n minus 2 terms are going to cancel, n minus 3 terms are going to cancel, 1s are going to cancel, everything is going to cancel apart from this time the n and the n minus 1 from the top. We're going to have an x squared on the top, and we're going to have a 2 factorial on the bottom. So let's write that down. We're going to have n times n minus 1 times x squared over 2 factorial, which is just 2. So you can write the factorial if you want. You don't really need that. It's up to you. You'll see that in textbooks. Some will write it, some won't. Let's do one more term. Hopefully you can start to see a pattern emerging. Can you maybe guess what the next term is going to be? Well, let's have a look. We're going to have n factorial on the top, n minus 3 factorial on the bottom, 3 factorial, and our x cubed. What's going to cancel this time? Well, this is again n minus 1, n minus 2, n minus 3, all the way down to 1. This starts at n minus 3, goes n minus 4, stops at 1. And what's going to cancel? Well, we're going to cancel the n minus 3s, the n minus 4s, everything down to the 1. And this time we are left with n times n minus 1 times n minus 2 on the top, our x cubed, and a 3 factorial. So let's add that in. n minus 1, n minus 2, x cubed over 3 factorial. And that pattern is going to continue forever. Now, bearing in mind that we're doing this specifically for when n is not a positive whole number. Normally, or well, not normally, when n is a positive whole number, these terms eventually stop. And the reason they stop is because we end up with a 0 in the formula version of the NCR. If we try to do like 5C6, we'd end up with a 0. And that's why these functions here, when n is a positive whole number, that's why they stop, that's why they terminate. When n is not a positive whole number, the functions will not stop. This will carry on forever because we won't have a 0 in the top. We won't have a 0 on the top here because it's going to skip it. It's going to go a half, minus 3 over 2, and so on. Or it's going to go, it's going to start negative, so we're never going to go past 0. Whereas if n was 4, it'd go 4 times 3 times 2 times 1 times 0, and that 0 term would be the term that makes it stop. So that's not going to happen. So that's one big difference between expressions, binomial expansions, where n is a positive whole number that terminates, and when n is not a positive whole number, and when n is not a positive whole number, these expansions will not terminate, they will be infinite. That doesn't mean we need to write millions and millions of terms down. They'll tend to ask for, say, the first 3 terms, so you'd stop here. Remember, 1 counts as a term, so that's quite useful. If they ask for 3, you only need to go up to x squared. Or they might say, do the binomial expansion up to x cubed, so then you know to stop there. They'll let you know in the question what you need to do. So that's our formula. The formula that we've got there, that's our formula. Now I've got some extras to tell you about that go along with this formula. I've just mentioned the first one, that the expansion terminates when n is a positive whole number, but any other value will lead to an infinite series. The other thing that's really important is that we can use these expansions to work out estimates for x. We will do more of this in lesson 2 or 3, but for now what you need to know is that these expansions will be useful for providing estimates as long as x is between -1 and 1. The reason for that is because as the powers of x increase, if you imagine x being, say, 0.2, 0.2 cubed is a pretty small number. 0.2 to the power of 4 is even smaller. 0.2 to the power of 7 is absolutely tiny and won't provide much help to an estimate that we, say, need to round to 2 decimal places or 3 significant figures. So we can use these as estimates and stop early and only work out 3 or 4 terms when x is a number between, and the rule is between -1 and 1, and that's so that large values of x become really tiny, become negligible, and so won't contribute much to the estimate. Okay, so you'll often see questions say work out the estimate or work out the expansion for what values of x is this expansion valid, and you just need to say it's valid when x is between -1 and 1. That's not always the answer, but I'll come to that when we see it. Okay, so I've got some examples that we can work through using the new version of the binomial expansion formula. First one I've got is 1 plus x to the -2. So x is just x and n is -2. So let's see what we get. We've got to go up to x cubed. The first term is going to be 1. The second term is going to be -2 for n and then x. Third term is going to be -2 for n. -2 minus 1 is -3. Then we've got x squared, and that's over 2. And the x cubed term is going to start with the -2. Take one off, that's -3. Take another one off, that's -4. X cubed over 3 factorial. Now I'm not going to write 3 factorial, I'm going to write 3 times 2. Now the reason I'm doing it like this is because I like to, rather than grab the calculator and try and work all these numbers out, which can become quite difficult when you've got like -2/3, -5/3, -8/3 and so on. I like to cancel as much stuff down as I can. I'm going to cancel, well, let's go one step at a time. Here I've got 1 and I've got -2x. Right, let's look at the third term. On the top of my fraction, I've got 2 minuses which I can cancel. I've also got a 2 on the top and a 2 on the bottom. That's going to cancel as well. So that's going to leave me with positive 3x squared. The next term, is it going to be positive or negative? It's going to be negative because I've got 3 minus signs. Then I'm going to cancel what I can. I can cancel that 2 with that 2 and that 3 with that 3. So that leaves me with 4x cubed. And I've gone up to the x cubed term, so that's the final answer for that example. Okay, let's make it a little bit more difficult. Sorry, I'm just going to bring in the formula so we can look at it as we talk. Again, like with all of these questions, you might want to have a go first and then see if you've got the right answer. If you're not feeling confident yet, just watch what I do. So, first term's 1. Second term is going to be n times x. Now this time my n is 3 over 2 and my x is 3x. Now it's really important to put that in brackets so that you remember to apply the powers when necessary. I'm not going to work anything out yet, I'm going to simplify it all afterwards. So the next term is going to be n, which is 3 over 2, times n minus 1, which is a half, times x, which is 3x, squared, divided by 2. And the next term is going to be 3 over 2 times a half, times minus 3 over 2. I need to take another 1 off that, times 3x all cubed over 3 factorial, which is 3 times 2. Okay, the first two terms aren't going to be very difficult to simplify. Sorry, I need a plus in there. But these are, and I'm going to talk you through how we simplify those. Try not to pick your calculators up. But let's see how we get on. So, first thing to recognise is that this is going to be the top of my fraction and this is the bottom of my fraction. So the top is going to be 3 times 3, which is 9. So that's 9 over 2x, or 9x over 2. The next term is going to be positive. Now the top of my fraction is going to be anything that's right on the top of a fraction. Whoops, I want yellow for that. So that's the 3 and the 1, and this 3 here. Remember, that's being squared. The bottom of my fraction is going to be the bottoms of those fractions and that denominator there as well. So what I can cancel anything yellow with anything green. Now there's not actually anything that can cancel there. There's no 3's in yellow and in green, or 2's in yellow and in green. So I can just go ahead and work this out. 3 squared is 9, times 3 again is 27. And on the bottom I've got 2 times 2 times 2, which is 8. And that's going to be x squared. Okay, let's have a look over here. Tops, 3, 1. Remember that minus sign? Let's put that in now. It's the only minus sign, which means the term is going to be negative. So we'll put that in. Top cubed, let's remember that. Bottom of my fractions, 2, 2, 2, 2, and a 3. So what can cancel first? I can cancel 1, 3 there on the top with a 3 there on the bottom. And again, that's the only thing that can cancel. So the top of my fraction is going to be 3 cubed, which is 27. The bottom of my fraction is going to be 2 times 2 times 2 times 2, which is 16. And that's going to be x cubed. So that's the expansion up to and including the x cubed term for 1 plus 3x to the power of 3 over 2. So you should now be able to work through exercise 4a. I've also added in an exam question just so that you can kind of see what you're expected to be able to do at this point. This is exactly like we've just practiced. This one's a little bit more difficult, but notice they follow on. And it's quite a big number of marks, an 8-mark question in total. Hopefully what you'll find is this is one of the easier topics of year 13, and this is where we're going to collect a lot of marks. 8 marks on a pure paper could be like a third of a grade. So if you can nail this question, then that's going to take you a long way to improving your grades, especially if you're struggling at this point in the year. So why don't you have a go at these 2 parts before I go. I'll talk through part 1 and then I'll give you a bit of time for part 2. or you can do all of it in one go and then just watch the end of the video. So, expansion of 1 plus 2x to the power of a half, up to and including the x cubed term. That's going to be 1 plus n, which is a half, times x, which is 2x, plus n times n minus 1 times 2x all squared over 2, and then a half times minus a half times minus 3 over 2 times 2x cubed all over 3 factorial, which is 3 times 2. Simplifying that, these 2's are going to cancel, so it's going to be 1 plus x. For the third term, I've got a 2 squared on the top, which will cancel with 2 of my 2's on the bottom. So that's going to go with 2 of them. So I'm going to be just left with a negative a half x squared. Next term, tops, we've got some 1's, 2's and 3's, and on the bottom we've got some 2's and 3's. So what's going to cancel this time? I've got 2 cubed this time. That will cancel with these 3 2's here. I've got 3 on the top and on the bottom. What about the signs? I've got 2 minus signs, so it's going to become a plus. All the yellow stuff's cancelled, so that's just going to be x cubed. That's going to be a half x cubed. So that's the expansion for part 1. Part 2 then says, hence find the expansion up to and including the x cubed term of this. Now this is a really common exam question. What the trick is to realise that we can rewrite the denominator as 1 plus x to the power of minus 3 on the top of a fraction. So we can times the 1 plus 2x to the half by 1 plus x to the minus 3 and then multiply these two together. Now I've already expanded this, so if I now expand 1 plus x to the minus 3 up to and including the x cubed term, then I'm going to have some stuff that I can multiply together. 1 plus x to the minus 3 is going to expand to 1 plus minus 3 times x plus minus 3 times minus 4 times x squared over 2 plus minus 3 minus 4 minus 5 x cubed over 3 times 2. That's going to simplify to 1 minus 3x. It's going to be a plus on the next term. That 4 and 2 will cancel to just a 2 on the top. So that's going to be 6x squared. The next term is going to be negative. That 3 is going to cancel. I can cancel the 4 and the 2 again down to a 2. And that's going to leave me with 2 times 5, which is 10x cubed. So, where we've got to multiply these two together, we're not going to. We're going to multiply 1 plus x minus a half x squared plus a half x cubed by 1 minus 3x plus 6x squared minus 10x cubed. Now, we don't have to multiply all of that out because we can stop when we get to x cubed. If I'm going to multiply something and get an x to the power of 4 or 5 or 6, I can ignore it. So I'm going to multiply the 1 by everything here, then the x by everything here, until I get an x cubed term, and then I'm just going to stop. So 1 times all of this is just going to be the right hand bracket. When I times the x by all of this, I'm going to get plus x for the x times 1. I'm going to get x times minus 3x, which is minus 3x squared. I'm going to get plus 6x cubed when I times the x by the 6x squared, and then I don't need to multiply the x by the 10x cubed because that's going to give me an x to the power of 4 term, which I don't need. I'm then going to come in and bring in the minus a half x squared. Minus a half x squared times 1 is minus a half x squared. Minus a half x squared times minus 3x is going to be plus 3 over 2x cubed. And again, that's as far as I need to go, because when I times it by the 6x squared term, that's going to give me an x to the power of 4. Times it by the x cubed term, it's going to give me an x to the power of 5. Don't need them. Last term, I'm just going to need to do the half x cubed times the 1. I don't need any more because they're going to give me 2 higher power. Notice how I've written this. I've lined all the terms up so that the x to the power of 0 terms are there, x terms, x squared, x cubed. And then I can kind of do some column addition to add these together. Minus 3 add 1 is minus 2. The next term is going to be 6 minus 3, so that's 3 minus a half, that's minus 2.5. No, it's not, it's positive 2.5, or positive 5 over 2 x squared. The next term I'm doing minus 10 add 6, that's minus 4, and then if I add those two together, that's 2, so minus 4 add 2 is plus 2 x cubed. So that's my final answer for that 8-mark exam question. Okay, so as I said before, have a go at exercise 4a, and I will put another video up going through the next part of the work.